Welcome back. Now we're going to talk about differentials. So the concept of error leads us into differentials, and we want to consider what they were, maybe going back to single variable calculus. So what we know is that dx and dy, those are independent variables. Often, we can represent dx as some delta x. We think of that as being a change in x, or rather x minus x naught. The same with dy being a change in y, or y minus y naught. Trying to write an x there, y minus y naught. So thinking about these, if we move some point x naught, y naught, to a point dx units or dy units away, but is still nearby. So the change in the linearization of f, that is called the total differential of f, and that's what this df is. It's the total differential of f. And that's calculated by taking partial with respect to x at the point times dx, that small fraction differential off of x, and then the partial with respect to y, evaluated at the point, times dy. So again, df is called the total differential, and what that is telling us, that is the change in the linearization of f. So differentials provide us with a way of estimating the amount of function changes as a result of a very small change, this plus dx or plus dy. Again, those are representing really tiny values as a result of a really small change on those input values. So, if we go back to where this was all introduced to us in Calc 1, we would always say dy dx. This was the Leibniz notation for derivative. But dy and dx really didn't have their own meaning. We started to toy with the fact that we could move them around when we began talking about integration. But now in Calc 3, we're going to kind of treat them as their own independent variables. So let's look at an example. In this example, we are going to be dealing with a cylindrical can. And it's designed to have a radius of 1 inch and a height of 5 inches. We're going to imagine that the radius and the height, however, are a little bit off. The radius is off by a differential of positive 0.03 or positive 300ths, and the height is off by a differential of negative 0.1, so negative 1/10. We want to estimate the resulting absolute change in the volume of the can. So we're dealing with volume. The first thing we need to know is the volume of a cylinder. So this is a right circular cylinder. The base here has an area of pi r squared. So it's the area of the base times the height. We can say the volume is pi r squared height. Now, for us to calculate this differential, it's not a function of f, it's a function of v. So delta v, or rather my differential for v, that's going to be the partial of v with respect to each of my independent variables. The partial of v with respect to r at some point r naught h naught times dr, which is given, plus the partial derivative with respect to h at r naught h naught times dh. So we need to know what r naught h naught are, and if we think about that as an ordered pair, r naught h naught, I'm going to let r naught be 1 and h naught be 5. So this is going to be 1, 5. So I need to calculate my partial derivatives. Partial v with respect to r, that's going to give me 2r. So I'm going to have 2 pi RH, circumference times height, and the partial with respect to h, that means pi r squared is a coefficient on h, so we just get pi r squared. Evaluating each of these at those points, I'm going to have 2 pi times 1 times 5, which is 10 pi. For the partial with respect to r, partial with respect to h, we have pi times 1 squared, we just get pi. So dv equals 10 pi times my dr value, which was given, positive 3/100 plus v sub h, which is pi, also times that given dh value, which is negative 0.1. And if you type this in your calculator, you get 0.6283185,307, or roughly the change in that volume is 0.63 inches cubed. And that represents how much we could expect the volume to be off if we knew the radius and the height were off by these small measures. So that's our video for calculating differentials. Have fun, be safe. As always, email me with questions.